Good morning, Year 12 again. So this was the question that I asked you to have a look at the very end of Tuesday's video, and it's about deciding which of these three options, which of these three types these were. And remember, strictly, if it's a one-to-many, it's not strictly a function. I mean, I think that's an unnecessary distinction, but there we go. And I find this really confusing. If I've got this here, not for your benefit, but for my benefit to help me remember. I don't know if I can give you a little thing that I sometimes use to help. If I can draw a line like this for a single x value and that has more than one y intersection, that means I'm dealing with this. A single x value has more than one y value. So that would be one-to-many. If, however, I can draw a line across a function and it crosses the graph more than once, so if there are more than one x values that give you the same y value, then that's many to one. So I don't know if that helps. And remember, if it's both, like the circle, that trumps it, one-to-many. So because there are several places where I can draw a vertical line that crosses this graph twice, this is a one-to-many function, except it's not really a function. Here, for every x value, there's only one y value, so that's a one-to-one or one-one function. Here, no places where I cross the graph more than once that way, but I can intersect the graph twice there. Not everywhere, but in some places. So that means we're dealing with this situation here. Sometimes you've got two x values giving you the same y value. Here and here give me the same y value. So that's many to one. Here, no places there, but yes there, so that's many to one. Here, I've got a 1-1 function. Obviously the domain is limited, can't be that value, but for the values that it is defined for, it's a one-to-one function, and ditto for the last one, 1-to-1. Hope that's okay. Let's move on. Okay, so here's where we're going with this today. Have a look at this question here. There's a couple of things that are different here. Firstly, we've got this rather odd notation here, and this is just another way of writing this. What we're saying is there's a function where x is taken and you do 5 take away 2x or x squared plus 3x. So this is just another, goodness knows why we have several ways of doing it, I don't know. We've got y equals f of x equals, and now this f colon x arrow equals. It just means this is a function. And the other thing is that this function is defined differently for different domains. So when x is less than 1, it's this, and when it's greater than or equal to 1, it's this. So have a think about what the graph of that is going to look like, and have a go at sketching it. Pause and have a go. So what I've done here is I've sketched, ignoring this limitation, I've just sketched the graph of 5 minus 2x. Y equals 5 minus 2x, goes through 5, gradient of minus 2, and I've worked out the x-axis intersection by asking what you get when y is 0, so that's 2.5. And I've done the same for x squared plus 3. I know that's just the x squared graph shifted up 3. Now, 1 is the key x value, isn't it? So when x is 1 with this function, the function is 3, so I know that this goes through 1, 3. And it's defined as this for all values less than 1. So the graph is defined as this straight line all the way down to, but not including that point there. So how do we show that? This is going to be my big graph here with everything on. Well, we show it like this. Here's 5. I've got my graph coming down, and I have an open dot. Do you remember that from inequalities? An open dot at the end of that line, because that line goes all the way down to, 0.99999, but not actually to 1. Okay, so when x is equal to 1, we jump to this function. Now, when x is 1 in this function, y is 4. So I know that that's going to go through 1, 4. And x can be 1 now. So when we get to 1, we jump from that point to this point. And I'm going to put a closed dot there because it can actually be that value. And don't forget, the graph is curving up like that, so it's going to look like that. So this is this rather weird function defined by this. And we're then asked to state the range, so that's the y values. So this function will have y values which are always greater than 3. It can't be equal to 3. Remember, this definition doesn't include 1. So the range is that f of x is greater than 3. And solve f of x equals 19. Well, I've plotted the f of x graph, and so I've plotted y equals that, albeit rather odd. I now just need to plot y equals 19, which is not to scale this, obviously, but that's a horizontal line that goes through 19. And I can see that that intersects my graph twice. It intersects this part of the graph, and it intersects that part of the graph. So there are 2 solutions to part B. My first solution, I'll call it solution A. That's when this equals 19. And my second solution, B, is when this equals 19. So I can just solve those. So I'm going to minus 2x, take away 5, is 14. So x is minus 7 is one solution. And take away 3. So x is plus or minus 4, but we know on this branch that x is always greater than or equal to 1. So I'm just going to say, right, x is 4 is the other solution. So we've got a discontinuous function here with 2 parts to it, and we've used that to solve a problem. Let's move on. Here's a really weird question where we've got a function, h, but we're not given any algebra for it. So we're asked to sketch it, but we're not given any algebra for it. We are just told it's linear in 2 sections, and those 2 sections actually overlap because they both go through the point minus 4, 2. Now I'm going to have a go at sketching this, but I'm already feeling like I'll probably need to apologise. In fact, I'll just reach for a ruler at this point. So minus 4, 2 is the key value here, so I'm going to go along to minus 4, 2. And the graph goes in a straight line from minus 10, 14. Right, I'm already apologising because this clearly isn't going to be to scale, is it? Minus 10, well, 14 will be up here somewhere. So it's a straight line from there to there. And it's also linear from minus 4, 2 to 627. Oh dear, right, so 627, that'll be something like 6, and then 27 will be up here somewhere. So goes like that. And that's it. The function doesn't carry on because the previous one, which I've lost, where's the previous one? Right, so the previous one, that did carry on up there forever, and this one would have carried on up there forever. But with this one here, no, it just starts there, goes to there, and then carries on to there. So there's no open and closed dots because it actually goes through those points. So the range, well, that's the y values. It does equal 2 this time. So h of x is always greater than or equal to 2. It never drops below 2 as a y value. And find the values of a such that h of a equals 12. So we plotted the function, and we now just need to plot the y equals 12 line, which is here. Now, I've been a bit clumsy here, haven't I? I don't know exactly how that's going to be. So Do you want to have a think about how you could answer that question? It's a 4-marker, so it's probably going to involve a little bit of work. Pause and have a go. Now, as is often the case, I'm sure some of you will have come up with a more efficient way of doing this than I have, but I just worked out the equation of the two line segments. So this line here, I worked out the gradient. So from this point to this point, that's just a sketch there, I worked out the gradient's -2. And I had 2 points, so I had gradient and point. I could work out the equation. So I said, right, y is -2x plus something. I substituted in that point, found that c was -6. So that's the equation of that stretch of the line. And I want to know when that stretch of the line crosses the y equals 12 line. So I just said, when does this equal 12? And I got -9. And although my sketch is pretty clunky, that could potentially be -9. So yeah, I'm happy with that. I did exactly the same for this stretch, uphill line, so I'm expecting that to be a positive gradient. And it was 2.5, 5 over 2. So I said, right, the equation of the line is 2.5x plus something, substituted in that point. That something was 12. So it crosses the y-axis at 12. So where does it cross the y equals 12 line? Well, it's at 0. So I was quite pleased with myself, because actually, although this diagram was pretty clunky, it does look like it's intersecting fairly close to the axis. So the two solutions are that this funny straight line crosses this line when x is -9 and when x is 0. Those were the two solutions. Well done if you use that way. Well done if you came up with a solution of your own. Okay, here's one more to try. Have a go at sketching this one first. 0 is the key value, so that makes it quite nice and easy. And remember, when drawing that, I effectively think of that as -x plus 10. That's the way I think of that one. So pause at this point and see if you can sketch it, and then we've got a couple of solving questions to do. So you might feel confident to carry on and finish it. I'm going to come back and show you my sketch and do B and C with you. Okay, so this line here goes through 10 on the y-axis, has a gradient of -1, so it would look like that. And of course it would carry on up here, except we're saying that x is only bigger than or equal to 0. So solid dot there, and it goes down there. When x is less than 0, we switch to this function. That's the y equals x squared parabola shifted down 6. So it can't actually be 0, but it can be anything slightly smaller than that. So I do an open dot with the parabola going up. So the good news about that is find the values where it equals 43. Well, this line never equals 43, because the highest it reaches is 10. So I've only got to worry about this curve here, which will eventually go up and get to 43 on the y-axis. So the solution for part B is just when x squared minus 6 equals 43. And I know it's going to be a negative value, because x is always negative here. So I'm going to add 6. Square root of 49 is plus or minus 7, but I know it's going to be minus 7 in this case, because this function isn't defined for positive values of x. So I've sketched s of x. We can use whatever letter we want. So I've sketched y equals that. So now to work out this, I need to sketch y equals that. So the y equals x line looks like this. And that's going to intersect twice. That's going to intersect here and here. So we're not asking now when does this equal a value. We're asking when does y equals x squared minus 6 cross y equals x. So I've got, for point A, I've got effectively y equals x squared minus 6 and y equals x. So I want to know where they intersect. So I'm just going to say when does x squared, and it's a quadratic, and oh, that's not a bad one, is it? So this is point A, which I know has to be negative. The x value is negative there, so that's my solution there. Point B, that's where y equals 10 minus x crosses y equals x. So I just make one equal to the other. And that's an even easier one. Add x to both sides. X equals 5. That makes sense. That could be 5, couldn't it? Yep. So I've got x equals 5 and x equals minus 2 as my two solutions there. Okay, so page 32, you will find the questions we've been doing. And here's the one I would like you to submit. So this is on page 32. It's another one of these discontinuous functions, but this time, unlike this one, which was only limited at 0, so it carried on forever there and forever there, this one, excuse me, is limited at both ends. So the function itself is only defined from -5 up to 4, so that's the domain of this function. And you've got two functions to sketch. Now, of course, you've got your calculator to help you, but I'm hoping you might be able to have a go. Y equals e to the x, like any exponential function, that looks like that. And when you replace the x with minus x, that's a reflection, and it's a reflection in that direction, so it's going to look like that. No, sorry, I've just sketched exactly the same function again. Sorry, it's going to look like that. Except, of course, it won't touch 0. I really shouldn't have started that, should I? Anyway, hopefully you'll be able to sort that one out. Anyway, have a go at submitting that, and one more video to go this term, this year. It's funny saying this year because we'll be back in 6.5 weeks' time. But yeah. Keep plugging away and keep in touch with any problems that you're having. Thanks for those of you who are. Take care.